For intuition, let's start with a simple idea. Imagine we have an input heap file like the one on the upper right. Now that heap file is showing individual values, where in a database we would probably have entire rows on these pages. So keep that in mind, that these values might be entire rows in general. We're going to sort this heap file, and we're going to sort it by the search key that we want to fetch things on, that we want to index on. Okay? And we're going to leave a little space for future inserts. And so what we're going to get is a file that looks like the one below. It's physically ordered with the pages storing data in the correct logical order for us to search on. And so we'll be able to do sequential access in this file from left to right and get the data out in the order that we want to search on. Now, do we need next pointers in this file to link these pages together? The answer is no. The pages are physically sorted in the logical order of data that we're going to want to search on. The second step we're going to do in just a minute is to build an index file on top of this file. But before we do that, let's answer a natural question. Why not use binary search to search through this file that we just built? After all, that's what we did in the previous lecture with sorted files. Well, one answer is that binary search, if you remember, induces a binary tree over the file, where in essence you can go left or right at any given decision point. Now, a binary tree is going to create a tree that's log base 2 the number of pages high. And log base 2 is going to still give us a tree that's pretty tall, maybe 10 or more levels tall for our data. That is a lot of IOs to just fetch a single record. We'd like to do much better than that. And so we want a tree with bigger fanout. Another issue, if you think about it, is that these records that we're storing may be big. You might have big records out of which the search key is only a small attribute. So is there something clever we can do by taking advantage of the fact that the search keys themselves might be quite a bit smaller than the records? So the first natural thing to do is to build a search file for our file. So we're going to start with this file up above. And this is a file of key, page ID pairs that is sorted by key. So you can see there's a 1 and a page ID that points to the page that starts with 1. There's a 3 and a page ID pointing to the page that starts with 3, and so on. This is going to be better. This is a much smaller file than the original file, and we can do binary search in this much smaller file. So we already have a win. Note that this isn't actually the layout of this. I forgot in this picture to break this file into pages. It actually looks something a bit more like this. Okay, but given this file, we can do binary search in that, and that is better. But we should ask ourselves the question, what's the complexity of search in the file up above? And the answer is, it's the same complexity that we had before. It's still binary search, and the file up above is only a constant factor smaller than the input. If we add data to the input file, the file up above will grow linearly with the data we add to the input file. Because all we're storing up above that's smaller is we're skipping a constant number of values per page, and we're only keeping the search key bytes out of each record. So those are constant factor wins. However, what we might do then is do this recursively. We'll build a search file for our search file now. And up here, what we've got again is key pointer pairs, where the key is the low value on the page we're pointing to, and the pointer points to a page. But now this is over the actual index file we built before. So we can do this recursively until we get an index file up top that's only 1 page big. We're going to have an invariant here, though, that for any node in this search tree, so any one of these pages, it's going to be a bunch of key pointer pairs. And in particular, somewhere in there, there's a key pointer pair for left and a key pointer pair for right, L and R in this notation. We have to ensure the following invariant. All tuples k between KL and KR are on the left-hand side. And notice the less than equals to and the less than in this expression. So this key 7, for example, all things that are less than 7 are to the left of it. All things that are greater than or equal to 7 are to the right. Okay? So greater than or equal to the right, less than to the left.